Okay, so I'm going to talk to you about big data analysis. So you've heard the term big data once today already, and I guess many of you probably hear this in your daily working life as well. So people mean different things by big data. Some people like to use the term big data when they're just using data because it sounds a bit more fun, I suppose. But what I'm going to think of as big data here is the size of the data is such that the computational considerations become really important when you're choosing what sort of technique you're going to use on that data. So what you might usually do when you have a small amount of data is you pick the technique which is going to be the best from a statistical perspective. But with big data, with an enormous amount of data, you really need to pay attention to what computational resources you have available, and then try and pick the best techniques subject to those sorts of constraints. Now, rather than give you an overview of sort of issues in big data, I'm going to talk about a particular project which I've been working on with Nikolai Meinshausen, who's at ETH Zurich. And this is a problem of a large-scale classification problem with binary data. So this is an example of the sort of problem that we were thinking about. I don't expect this to be a realistic example, but hopefully many of you will have sort of more realistic versions of this sort of problem. But just imagine this problem here, where imagine you've got a shop, and customers come in, they buy different things, and you record what the different customers buy. And suppose the customers are divided into two groups. Maybe these are customers who have a loyalty card or something, these people don't. Or perhaps you've just, out of your database of all the purchases which customers have made, you query something like which customers bought bread and which customers didn't. So maybe these are the ones who bought bread and these are the ones who didn't. And we want to try and find out what's different about the purchasing behavior of the customers in this group compared to the other group. And more specifically, we want to find out whether there's some collection of items that's often brought together within one of the groups, but only rarely in the other group. And there are other sorts of instances of a similar sort of problem. You could imagine, rather than having customers here, you've got different documents in two different groups. And here you've got the words, or pairs of words, or triples of words contained in those documents. And you want to find groups of words that occur frequently in one class of documents, but infrequently in the other class. So maybe these could be emails, these ones are spam, and these ones are not, and you want to build some sort of spam filter. You want to find out which words occur more often in one class, but not often in another. Okay, so that's the sort of problem that we're thinking about. Here's another representation of the same data. Here we've got a grand table where along the top we've got all the items which were available in the shop, and here we've got the different customers and what they bought. So 1 means that this person bought cheese, this dot was meant to represent a 0, so they didn't buy a cereal, they didn't buy a book. You get the picture. Okay, so if we're trying to find, for example, collections of items of size 3 which are bought often together in this top group but not in the other group, what we could do is just look at subsets of these items of size 3 and just check how often are the things here bought together compared to down there. We may find that here we don't really get anything interesting. Look at another subset and continue and so on, and we end up with something like this maybe at the end after searching through these subsets, and this perhaps looks interesting because it seems as if in this group these people have bought cheese, eggs and milk, whereas here nobody seems to have bought all of those things together, which may or may not be interesting. Now the problem with that sort of naive approach in a big data setting is that when the number of different variables, the number of items that you've got is very large, then the number of subsets that you're going to have to search through is going to start to become very big. So roughly you'll have, if you've got p variables, you'll have roughly half p squared subsets just of size 2. If you're looking at subsets of size 3, it gets even bigger. And in general, it's sort of order p to the d if you're looking at subsets of size d, or d-way interactions as we would call them. So for example, if p was 10,000, then the number of two-way interactions is going to be around 50 million, and three-way interactions 100 billion. You look at larger and larger sets, and you can see things are going to start to get quite bad for your computer. So what people often do, or the standard sort of way of dealing with this issue, is to try and restrict the search space. You don't search through all of the different possible subsets. What you do is look at individual variables, and you look at this particular variable, and you say, is this variable by itself different in one group compared to the other? If it is, then you start looking at interactions or items involving this item as well. So collections of items involving that one as well. Maybe this one isn't interesting, so you move on to the next one. If that's not interesting, you move on to the next one again, and you think, okay, this is maybe a bit interesting. There seem to be more people here who bought cheese than the other. Let's look at collections of items involving cheese, and you go through this way. Eventually, you might end up looking at cheese and eggs, and you think, oh, this is pretty interesting compared to the bottom half, and you might eventually end up with the same sort of result. And this is basically the way that something like a decision tree would work, a classification and regression tree. Basically, these build up these sets incrementally, starting from smaller sets, and then you add on variables or add on items until you get something interesting. And really, most other most other methods work in a similar sort of way. But this won't always work. I mean, it often does work in practice, but you can easily have a very strong interaction term which you might not found, because none of the marginal effects, none of the individual variables are by themselves interesting, but together a whole collection of them might be very important. So here is a sort of a toy example or thought experiment where you can see that this method wouldn't work at all. So imagine you start out creating a matrix with just ones and zeros. And what you do is for each entry in the matrix, you flip a coin. If it comes up heads, you put in a 1. If it comes up tails, you put a 0. Okay? So you've got this great big matrix. And now imagine trying to split the rows of that matrix into two groups by looking at just the first two columns. And if the first two columns agree, you put them in one group, group A. And if the first two columns disagree, or those two entries disagree, you put them in the second group. So what you end up with just for this first group is a matrix which looks like this, where here you've just got a sort of random allocation of 1s and 0s. And if you look down just one of these columns, you've got a random allocation of 1s and 0s. But if you look at these two columns together, you can see that they're always the same. And in the other sort of group, the first two columns will always be different. Okay? And now, the issue with looking at variables individually here is if you look at any variable by itself, it will look exactly the same in this group as compared to the other group. You'll sort of have half of them will be 1s randomly allocated across the rows. And there's nothing special about each individual column. So you won't really be able to restrict your search space that way. You actually have to start looking at pairs of variables together. So you're really going to have to look at almost every pair to pick up that these two are important. So another way of approaching this, which doesn't seem to have been done by anyone actually, but it's quite a neat idea, I think, is to look at rows rather than columns. So just pick a random set of rows here and ask the question, what is common amongst all of these rows? Okay. So if we look at what's common amongst all of these, we see, oh, there's a 1 in all three of these, there's a 1 in all of those. Here, there aren't 1s across all of these, there aren't 1s across all of these. And if you remember, we transformed what we had initially as sets here, sets of items, into 1s and 0s. So what we're asking for really is in the intersection of these sets. And if you look at the intersection of these sets, you immediately just end up with these two variables. Okay? So you might of course not have picked those if you were picking a random subset of rows, you might not have picked them. You might get unlucky. So here, if you take the intersection, you just end up with the empty set, or you end up with just this variable here, which might not be interesting. But you can see that there's a certain probability, at least, that if you were to select the right rows, then you get this intersection, you get this interaction coming out. Now there's a way to speed this sort of thing up. So actually, although it looks as if this is going to do better than the brute force search, it doesn't. The complexity of the algorithm doesn't actually end up being better, because computing the intersections actually requires some computational effort. But you can really speed things up if you notice that computing intersections between large sets, although that's time-consuming, computing an intersection between a small set and a large set is very, very quick. Because what you do is, in your small set, you just ask the question, if you look through each element in your small set and you ask the question, does this appear in the larger set? And all you need to do is a bisection search in the larger set to check whether it's there. So you sort of incur a log factor for the larger set. So what we should try and do is reuse the intersections between the large, reuse the intersections that we've calculated between large sets. So here's a quite literal toy example to try and illustrate this idea. So here we looked at some tic-tac-toe data. So I assume everyone's familiar with the game with noughts and crosses. Well, here we've got black circles and white circles. It's the same sort of idea. And this is essentially a binary data set, because what you would do is you would have a variable for, does this square contain a black circle? If it does, you put a 1. If it doesn't, you put a 0. Then you say, does this contain a white circle? If it does, you put a 1. If it doesn't, you put a 0 there. So, okay, so this is just binary data. Thanks. And the issue is here that the marginal effects are weak. So you can't really look and say, well, if this contains a black circle, then someone is likely to have won the game, right? You can't really tell just from looking at an individual square whether someone has won. You actually need to look at the whole thing together to find these winning combinations, which are these 3 in a row. So the way that we try and reuse the intersections between large sets is by putting the search in a tree structure like this. So what we do is pick a random observation from one class, and then we intersect it. We picked one random observation, then we pick some other random observations here. We intersect that with that. So ask the question, what's common between this one and this one? And we end up with something like this. And then we pick some other random observations and ask the question, what's in common with this and these other ones? And we go down and we end up with something like that. And carry on, and we end up with, well, here we've got a 3 in a row, which is what we want. Okay? And so what's happening here is here you've got intersections between larger sets which take up more time. As you go down the tree, you have intersections between small sets and larger sets, which is much easier to do. And so we can analyze the complexity of this algorithm, and for example, we can show that in the coin flipping example which we had earlier, the number of computations is actually just of order p, rather than the p squared for a brute force search, if you had to look through all of the different pairs. And more generally, whenever the prevalence of the target interaction that you're looking for is quite high and the data is sparse, so there are actually many zeros in your data set, then this algorithm, which we've called random intersection trees, works really quite well and often beats the other sort of competing methods. One last thing that I'll mention is that so what happens is from one class you end up with this candidate interaction, and then you have to check in the other class whether how often does this thing that I found from my first class actually occur in the other one. Because if it occurs very frequently in the other one, then it's and just as frequently in each of them, then it's obviously not very interesting. And that check of actually evaluating the prevalence of an interaction in the other set can be quite time consuming, but we can speed that up with a technique from computer science, or a method based on a technique from computer science called minwise hashing, which is basically it acts like a compression scheme. It's quite an interesting technique, actually. We've also looked at compressing data sets and then applying regression on the compressed data. So if your data is too big to apply regression on immediately, compress it using the technique like this, and then apply your regression. And we've looked at how well that does. And sometimes it can uncover hidden structures in the original data which you wouldn't have been able to find with just applying regression on the original data set. Okay. And that's about all I have time for. So that I think the two sorts of take-home messages that you can get from this little project are that, well, problems which can be simple in the small data setting can be quite interesting once you've got these computational constraints on the methods that you can use. So we have to revisit some of these simple questions and try and look at them in this big data lens. The other thing is that sometimes you need it's helpful to have some ideas from computer science and statistics together to actually tackle some of these big data problems. Okay, thanks very much for listening.